over 2 pi s in the negative field direction. So this I prime is the current. I prime is the current enclosed by S, by with a radius S. So how can I find that? Yeah, so I prime displacement current, okay, basically, yeah, the conduction current. This is the conductor, so yeah, so it's the conduction current. So that's gonna be, the total I, the total current I, S squared over R squared. The radius is A. Okay.
I'm
Yes.
getting the positive feed direction. Am I?
Okay, the current is, I think it should be, so X is towards U, so phi, positive phi is always measured from the positive X axis. Positive phi is that way.
Z is going to the left.
Yeah, I define my Z in this direction.
Oh,
Yeah.
okay.
Okay, so that's gonna be the current, so that will give you a magnetic field B equals to mu naught I prime, where I O S over 2 pi S squared along the minus phi direction. All right, so we have the magnetic field, we have the electric field. So we are interested in the power delivered by the source using the Poynting theorem. Okay, so the power delivered is just the work done per unit time. So this is what we want to find. So according to this, it's the rate of change of electromagnetic energy per unit time over that volume, over this volume. So the amount of electrical field, and if you calculate this energy, which is UEM, which is gonna be the epsilon naught over 2, the integral of the electric field squared d tau plus 1 over 2 mu naught, the integral of v squared d tau over the volume, what you'd find is gonna be, is it gonna be a function of time? This, is it gonna be a function of time? The final result, after, using this B field, using this electric field, if you evaluate it over this volume, then what you would find here is gonna be just a constant. Because we are considering the static case, so the electric field is constant, the magnetic field is independent of time. So therefore, what can you say the change of U? This is a constant. Is a constant. So that tells you UEM by dt is equals to 0. So, we know that the from our knowledge in intro physics, we know that there is an energy per unit time equals to the voltage times the current is being supplied to this system, right? So where does that energy go? So it's carried by the electric field. So we have to carry out this and see if that actually gives us the voltage times the current. So what's, yes?
For the energy of the electromagnetic, the UEM,
Uh-huh.
does that just come from the sum of the
Yes, the
energy.
sum of the magnetic field over the volume. So you can carry out this over this volume, and you would find a constant value which is independent of time. So this term is going to be zero. So, but we know that the battery here supplies energy every second. That's equals to the voltage times the current. So, where does that energy go? So basically, that energy is carried by the electric and magnetic field leaving the surface of this conductor. So let's find out that. So in order to find out that, we need to find the pointing vector. So what's going to be the pointing vector? S. We have this for magnetic field, electric field, sorry, B over L along the negative direction, and a magnetic field along the v direction, which is mu naught I S over 2 pi S squared minus v direction. Yes. So what do you get when you take the cross product of these two? Yeah, so mu naught I A B times S over 2 pi S squared Z cross phi S P Z Z cross with phi, I get minus S. Huh?
What happened to L?
L, yes, it should be there.
And your
One over
mu naught.
mu naught? It should be
It should
positive.
cancel out mu naught.
So 1 over.
Yeah, from your pointing vector, it's 1 over mu naught.
Right, right. Over here.
Yeah, yes, thank you. One over mu naught. So now let's calculate this. So this tells you are integrating it over an area. We know that the pointing vector is energy per unit area per unit time. So you need to integrate it over the entire surface that encloses this cylinder. So if you do that, then you can find this term. So that what should you expect for this? Okay. Huh?
The only contribution would be from the curve surface, wouldn't it?
Yeah, but what would you expect the result at the end? This, when you carry this integration over the well, if that's zero, if this is zero, then where does the energy go? Yeah, it's okay. So what would you expect physically? You know for sure this much energy per unit time, power equals to voltage times the current, is being supplied by the source. So that's the rate of work done. Basically, that's this term. We know this is zero because the electric field energy and magnetic field energy is independent of time. So therefore, there must be some energy that's leaving this volume that's in the form of the pointing vector. So this term should give you this value. So that would be since we know that the pointing vector is radial and